All right, I just wanted to go over a couple of these homework problems because some of the stuff will be on the final, this moment of inertia stuff. So here we go. So let's see if we can find the moment of inertia of this shape about that x-axis that cuts through it. So here's the process that you would use to do that. First thing I'd like to do is find the information that I need to work through things, areas and distances. Okay. So I just find the areas. I've got two rectangles. The first one's 36 by 42, so that's an area of 1512 square centimeters. The other one's 12 by 12. That's the smaller one up here. I'm calling the big one part 1, the small one part 2. Okay, and so 12 by 12 is 144 square centimeters for part 2 there. All right, now I'm going to use the transfer axis theorem on this. I know I'm going to have to do that because I'm finding the moment of inertia about this axis right here, and neither of the centroids of shapes 1 or 2 are on that axis. So I'm going to need to use that transfer axis theorem, which is I bar x plus AD squared. Now D is the distance from the axis about which I'm taking the moment of inertia about, which is that green XX axis, to the centroids of each of the shapes. Okay, so what I would do with that then is I would want to find that offset distance. Okay, and so the offset distance goes from the axis to the centroids. So for the large rectangle, the total height is 42, so half of that would be where its centroid is. That shape, it's kind of hard to see, but it's right down there. That would be at 21. Now the axis I'm using is 22.3 centimeters above the base of the rectangle. So the difference between the 21 and the 22.3 is negative 1.3. So that would be the offset distance from the green XX axis there to the centroid of a large rectangle. Now to get to the tall rectangle, or excuse me, the smaller rectangle there, I'm going to find this offset distance. Okay, now what that is 30 so I'm measuring up from the base, so I'm going to go up 30, and then the rectangle would be halfway up to 12, which is 6, so that's 36 high. And then I'll take away the 22.3, which is the distance from the base of the rectangle to the XX axis there. When I take that away, I get 13.7. That's this distance right here. So that's 13.7, and this other one is negative 1.3. So now I've got the areas, I've got the distances, so now I can fill in a table to find the moment of inertia of that shape about the axis. So what I do, I find I bar x, which is bh cubed over 12. That's this formula right there. So for the large rectangle there, I'm just going to go the base, 36 times the height of 42 cubed over 12, 222,264. The area of that shape is 1512. The offset distance is 1.3. So 1512 times 1.3 quantity squared is 2555. I'll add that to the 222,264 and I'll get 224,819. That's the total moment of inertia of the large rectangle about the x-axis. So I've got the bh cubed over 12 plus the AD squared term, the area times the offset distance squared term. I just add them up and get the total. Do the same thing for the small rectangle. I got 12 times 12 cubed over 12. Okay, that's bh cubed over 12. It's 1728. The area is 144. The distance is 13.7. So 144 times 13.7 squared is 27,027. I'll add that to the 1728 and get the total 28,755. So I can add these two numbers together, and that will get me the total moment of inertia, which is 253,574. The units on that are centimeters to the 4. In some applications, I want that to be meters to the 4, so I would just take 100 centimeters per meter, take the 100 to the 4th power, and divide by it, and I'll get 0.00254 meters to the 4. You could express the answer either way. Okay. We got a little bit more complicated shape here, but the idea is exactly the same. We also have a circular cutout there that we have to deal with. So I just want to find the areas of the shapes. Okay, I've got two rectangles. 1/2 9 times 6 is 27. I've got the circle minus pi r squared, which is negative 19.63, and then the area of that rectangle, 12 by 21, which is 252. Okay, so there are the areas of each of the shapes, the two triangles on the side and the circle in the middle, which is a cutout, so that has a negative area, and then the total rectangle. Then I'll find the distances from the axes I'm going to take the moment of inertia about, and there's two of them here. I'm doing IX and IY, so one axis comes through like that. That's 11.8 centimeters high. The other one goes right, splits the thing in half, which is kind of a y-axis there. So I've got an x-axis, I'll find I sub x. I'm also going to find I sub y, which cuts down the middle. All right, so I need to find the offset distances. All right, now let's find the offset distances from the y-axis first. Now the circle and the large rectangle have their centroids right on the y-axis, so there is no offset there. It's a zero offset, but the two triangles are offset from that y-axis. So to get to both of them, I go 6, and then for a right triangle, the centroid, which is where I'm going, for this shapes is at the third point, I guess you'd say, from the right angle. So that would be right about there, okay? So that is the base over 3. All right, so I go 1/3 of 9. So 6 plus 1/3 of 9 is 9. Okay, so it's negative 9 to the one for the one on the left, positive 9 for the one on the right. Though being as you're squaring those, the signs aren't that important. They kind of cancel out when you square them. Okay, now we need to find the distances from that axis. Now the x-axis, now we'll do that. We want to go to the centroids of the two triangles, the circle, and the large rectangle. All right, so we know that the x-axis here that we're working with is 11.8 centimeters above the base. Okay, we know that the centroids of the triangle, and from the base, we're going to go up 15. That'll get us to the vertex. So then we'll go 2/3 of 6 more. So that'll be 15 plus 2/3 of 6. So what's going on there is we are coming up this way, and we're coming from this axis, we're coming 2/3 of 6, which is 4. See, it's 1/3 of the base that way, which would be 2, but 2/3 so from the right angle it would be 2, but from the vertex it would be 2/3 of 6, which is 4. Okay, so that would be 15 plus 4, which would be 19. Okay, that's the height of the centroid of those triangles from the base of the figure there, right down here. Now, up to the x-axis is 11.8, so the difference is 7.2 centimeters for both. Okay. Now, you're given the centroid of the circle. It's at 15, so you just take away the 11.8 and get 3.2. Now, the rectangle, where that's at, is the total height of the rectangle is 15 plus 6. It's 21. Take half of that, you get 10.5. That's where the centroid of the large rectangle is. It's half of the height, half at 21, which is 10.5. Now the x-axis there is at 11.8, so when we take the difference, we get negative 1.3. Okay, so that's the offset distance from the x-axis to the centroid of the rectangle. All right, so we got that information. We just put all that stuff in a big table here. I'm doing I sub x first. So I'm finding the moment of inertia of the two triangles about their own centroidal axis. That's bh cubed over 36. Base of 9, height of 6. Okay, for those triangles. So 9 times 6 cubed over 36 is 54. The area is 27. The offset distance we found is 7.2. So 27 times 7.2 squared is 1400. So you're going to take 54 plus 1400 and get 1454. That's the total moment of inertia of each of those triangles about that x-axis we're working with. The triangle's a cutout, so it's negative. The formula for the moment of inertia of a triangle is minus pi r4 over 4, which is negative 30.7, again, because it's a cutout. The area is 19.63. We found that earlier. Offset distance is 3.2. So negative on the outside, 19.63 times 3.2 squared is negative 201. So the negative 30.7 minus the 201 is negative 232. That's the moment of inertia of the circle there about the x-axis. It's a negative number because it's a cutout. Okay, the rectangle then, base at 12, height at 21, so 12 times 21 cubed over 12 because it's a rectangle. That's the formula for a rectangle. That's the moment of inertia of that rectangle about its own centroidal axis. It's 9261. Area is 252. Offset distance is negative 1.3, so that negative will go in there, but it just squares out, so it doesn't really make any difference, okay? So that'll be a positive when you square the negative 1.3. Multiply that by the 252, you get 426. 426 and 9261, add them together, you get 9687. Add everything up, and you get a total of 12,363 centimeters to the 4. So that's the moment of inertia of that shape about the x-axis. All right, now if you're going to go about the y-axis, it's the same process. It's just the distances are measured in different directions, as are the base and the height that go into the formulas. So for the triangles, instead of using a base of 9 and a height of 6, you basically switch those. The base is now parallel to the axis. So if you're finding the moment of inertia about this y-axis, you'll define the base with that dimension there being parallel to it. So that's 6. The height then would be perpendicular to the axis, which would be 9. So 6 times 9 cubed over, and I have a typo there that says 12, but it ought to say 36. And that, I think the answer is good. I think I just have a typo on what I wrote up there. So that would be 121.5 for both of those. The area is 27. The offset distance, again, is measured in the x direction coming from the y-axis. So it's measured like that. We found it. It's 9. So 27 times 9 squared is 2187. You can add that to the bh cubed over 36 for the triangles and get 2308.5 for both of them. The area of, or excuse me, the moment of inertia of the cutout circle about its own centroid there is minus pi r4 over 4, negative 30.7. The area is negative 19.63, but there's no offset distance because the centroid of the circle is right on the y-axis. So the AD squared term zeroes out. Same thing for the rectangle, okay? So you just end up with a total moment of inertia of that is negative 30.7. For the large rectangle, the base again is parallel to the axis. So that base will run right there. And so that's 21. We'll call in the height perpendicular to the axis. So that's going that way. And that is 12. And so it's 21 times 12 cubed over 12. It's 3024. The area is 252, but there's no offset distance. So the AD squared term zeroes out. So you get 3024. And you add that to these values here. Add those all together. You get 7610 centimeters to the 4. 76.1 times 10 to the minus 6 meters to the 4 if you want to measure it that way. Okay, so that's a run through the two moment of inertia homework problems. Now, the other thing I want to cover here is the three-dimensional stuff. Now, this is at the end of your packet. There should be this page there. If I'm not mistaken, I think I've also got it uploaded in Moodle.